So thank you very much for attending this talk. The purpose of this talk is showing that we can learn a lot about functional programming in general and about Scala in particular by solving logic problems using Scala. And we have experienced this, I've experienced this in my undergraduate course on functional programming in Scala at the university, but also at the trainings that we run at Aula Computing. And in this talk, we will give some examples of what we do in these courses. So, but before showing these examples, how or why is it possible to use logic as a playground for programming practice in first place? Well, this is possible because there is a strong relationship between logic and computation. This relationship is known as the Curry-Howard correspondence. And it basically states that, for instance, the typed lambda calculus of Alonso charts and the natural deduction framework of Gensen, which is a logical framework. The other thing is a computer language. These are two sides of the same coin. Basically, they are the same system. For our purpose, Carrie Howard tells us that if we want to prove a tautology, we want to prove that some proposition is a tautology or that some logic argument is valid, we can do this using the natural deduction framework or another logical formalism, but we can also do this using a program. Okay, a program with certain characteristics. So, for instance, if we want to solve a given problem in propositional logic, then we need algebraic data types. If we need to solve a problem in first order logic, we need dependent types. In second order logic, we need generic programming and so forth. And it so happens that the Scala type system enjoys, to some extent, many of these properties, many of these features. We have dependent types, we have generics and so forth. We have, of course, algebraic data types. And in this talk, we will see several examples concerning propositional logic, first order logic and second order logic, of how we can use Scala to solve these logic problems. And in each case, we will stress which features of Scala and which techniques from functional programming we can learn. Okay, so let's go and let's start. Okay, with our first example. Let's say that we have to prove that this formula is a tautology in propositional logic. Okay, this formula says that if we have P or Q, then if we don't have P, then we have Q, which seems like a valid formula. What we will do first is to translate this proposition into a type. Okay, and into an algebraic data type in particular, following this mapping. This mapping tells us that propositional variables will be mapped into type parameters, that disjunction will be mapped into either, conjunction into tuples, implication into functions. The false proposition will be mapped into nothing, which is the type which has no instances. And since in logic we define not P negation in terms of implication, P implies false, not P in Scala will be represented as a function from P to nothing. Okay, so given this mapping, the algebra data type which is associated to this proposition will be something like this: will be a function from either PQ into a function from not P into Q. Okay, so this is the first step, translating our proposition into a type. Okay, following this mapping between propositional connectives and algebraic data types, different sum types, products, and exponents, and so forth. The next step, in order to prove that this proposition is a tautology, is to implement this signature. But to prove that for any P and Q, okay, for any P and Q, we can implement this function, which means that we can give an instance of this type. Okay, and how do we do this? In order to implement this signature, what we had to do first is to pay special attention to the different kinds of constructors and destructors of algebraic data types. The constructors tell us How can we create functions? How do we create tuples? How do we create aiders? Okay, and the distractors or observers tell us which information can we extract from a function using function application. Okay, what information can we extract from a tuple, from a product? What information can we extract from an aider, from a sum type using pattern matching? And how we can extract any kind of information that we like if we are able to obtain an instance of nothing. Okay, remember that nothing is a type who has no instance. If we obtain this nothing, is because we reach a contradiction. Everything explodes, and we are able to obtain anything. Okay. And moreover, what we will do is to, besides paying special attention and taking into account all these constructors and distractors of algebraic data types, what we will do is following a type-driven development discipline. Okay? Which means that we will implement the signature, filling the holes that we have in our program in a completely mechanical way, step by step, choosing a constructor or a distractor until no hole is left in our code. Okay, and this is something completely mechanical. Okay, this is something like a search procedure that we will do in order to implement this signature. So this can be automated, of course, but we will focus and play the algorithm by ourselves. So how do we do it? Okay, the first hole is the whole program. We have in this case is that we had to create a function. So in our first step, what we do is to choose the constructor of functions, which are lambda expressions. And our program will be like this. It can create a full lambda expression. The body, okay, will be there will be a hole in our body, in the body of the lambda expression, because we do not know yet how we will finish writing this expression, but for sure our program will have this shape. Okay. Next step, what we see now is that the type of the hole is again a function. So we, in a completely mechanical way, we write here our lambda expression schema. And now this next step will be a little more complicated. Why? Because the type of the hole is Q, and Q is a type variable. Q could be anything. Okay, it could be any type, and we do not have any constructor for creating Q. We have constructors for writing expressions of functions, for writing expressions of tuples and aiders, but if we do not have any of these types in our whole, we do not have constructors. So our only chance of being able to write an expression of type Q is by extracting information from the environment variables that we have in the scope. And what we have in the scope is this variable E and this variable MP, and choose one of the observers that we have in our table of algebraic data types. Okay. So what can we do in order to obtain which observer can we use in order to obtain Q? Well, notice that not P, it's actually, well, Q, first of all, is mentioned in the header. Okay, but let's follow a different route, because I would like to show how can we backtrack at some moment. Okay, so not P is actually P into nothing, function from P to nothing, and we know that from nothing we can obtain everything, including Q. So if I would be able, okay, to uh, apply MP to a value of type P, then I will obtain my Q. And this compiles. In every step of the type-driven development process, we obtain a fully well-formed program that compiles. Okay, and now this problem. The problem, of course, is how do we obtain a P? I had to observe the either and apply pattern matching. Okay, so let's see, let's do it in another cell. Okay, here, and we have two cases: the left case and the right case. Okay. Now we apply an observer in this case, and this observer, this pattern matching, provide us with new information. Now we have more information in our environment. For instance, we were missing an expression of type P for completing this code, and now in the left branch we see that we have P. So we are happy, and then we fill this hole. And what about the other hole? Our chances of obtaining an expression of type P, in this case, we already use all the information that we have available. So it can be possible. We have to backtrack. Okay, and backtracking in this case means, well, let's try another way. And of course, if we have to obtain something of type Q, this is very easy in this case, because what we have here is actually, okay, this information. And we already finished our implementation. And finishing this implementation means that, according to Carrie Howard, means that the proposition corresponding to this algebraic data type is a tautology. Okay. And if we are not able to implement this signature, this means that the proposition is not a theorem, it's not a tautology in this case. Okay, and it is because what Carl Howard tells us is that there is a one-to-one correspondence between this expression, this program, and the proof in natural deduction of the proposition corresponding to this type. These are one-to-one correspondence. And this is because in natural deduction, the natural deduction framework is structured around introduction and elimination rules for the different connectives. And this matches, this introduction and elimination rules match perfectly the constructors and observers of our algebraic data types. So this correspondence between the constructors and destructors and the rules of the natural deduction framework is what justifies that the either corresponds to the disjunction, that products correspond to tuples, and so forth. We won't see this in detail, how this correspondence between this program and the proof in natural deduction can be obtained, but it is something that it can be done automatically. Okay, from this program we can obtain a proof. And what if the proposition in question is not a tautology? For instance, let's say that we had to prove that this formula is a tautology, which is not. Okay? And you may say, hey, this is one of the De Morgan laws. If not P and Q, then either not P or not Q. Well, this is a tautology in classical logic, but it is not a tautology in intuitionistic logic, which is the kind of logic that corresponds to algebraic data type programming. Okay, so we will see. We will say something more about this in a minute. But now let's try to prove this the corresponding signature. Okay, for PQ, what we had to implement is the program corresponding to this proposition, which would be not P and Q. Then, okay, we have here a disjunction, not P, not Q. Okay, this is the program that we have to implement, and now we will do the same as before in a completely mechanical way. We will try, without thinking too much in the intuition, okay, of how to implement this signature in a completely blind process. We will try to fill this hole, this main whole of the application will has to be of this type. Okay? And in this case, what we have is a function. So how to proceed? Eventually, what we will see is that we will make no progress towards the implementation. Okay? We won't be able to fill all the holes that are constantly appearing. Okay, so what we see here is that we have not PQ. Okay, so this is my first step in the process. Then I have now to construct a type value of an expression of type either, and we have two constructors for this type. We have either left or right. Let's try any one of them. For instance, the first one, and this compiles. Now I have to create an expression of this type, but not p is a function from p to nothing. Okay. And so we use the lambda expression, the constructor for functions. And now we were in a constructor phase. We applied three constructors in a row. And now we had to write an expression of type nothing. We do not have constructors for this type, so we better get our nothing from the environment. The information that we have in the environment is not p, q, and p. Okay, and notice that, well, of course, we can obtain a nothing from p, but notice that not pq, not pq is a function from p and q and nothing. So we can obtain a nothing. How? Applying not pq to a value of type p and q. Okay? And now we are making progress and we are doing everything that we are requested. Okay. Now, in order to create a tuple, I had to use the constructor of tuples. Okay. And now p and q. Well, p, I have a p. But what about q? I do not have any way of obtaining q. But to use again this nothing. And using against this nothing will demand that we need P and Q in order to apply MPQ and so forth. So I will be again in a few steps. I will be again in the same place, in the need of obtaining an expression of type Q. Okay? So this is an informal argument that we can't implement this. We can implement this signature, but it is basically right. Okay, we can't. And informally, intuitively, it makes sense, because if we interpret this signature or this proposition in constructed terms, not in terms of classical logic, but in constructed terms, in terms of intuitionistic logic, what we are saying here is that when we have P, is that we have a proof of P. We have a proof of Q, we have a proof of P and Q, we have a refutation of P and Q, which means that if I have a proof of P and Q, then I can prove the absurd. We can prove the false proposition. We can reach a contradiction. But for that, remember that we need P and we need Q. From that, we cannot prove either not P or not Q, because if we attempt to refute P, what we have is only a proof of P. And in order to obtain a contradiction from this premise, we need both P and Q. So intuitively, it makes sense that we cannot prove this formula. Because when we are programming, when we write an expression of a given type, what we are saying is that we have a proof of the proposition corresponding to this type. Okay? So values, programs are proofs, and types are propositions. Okay? This is the way we read this. Now, this is not possible, okay, to implement. But if we can still use algebra data type programming in an intuitionistic logic to prove tautologies from classical logic. How? What we can do is to add a premise. To add a premise with a special formula, which it uses to be the law of excluded middle, in this case Q or not Q, but it could be also the double negation law and other equivalent formulas that provide us with enough information in order to prove this that this formula is valid, that we can instantiate this type. Okay, we won't do that, but I invite you to follow this example. And note that in this case, what we will have is that this is the law of excluded middle for Q, for this particular Q. Okay? And this is not always enough. Sometimes what we have to do is to use the law of excluded middle for any P. Okay? In such a way that what we have here is P or not P. But in this case, it can be proven with simply with the law of excluded middle applied to Q. Okay, so let's go for our next example. In our next example, we leave propositional logic and we enter in the field of first order logic. And we will in particularly use an example from Aristotle. We will use the Barbara syllogism and syllogisms in general. Syllogisms are logic arguments which are made from two premises and a conclusion. And in the premises and the conclusion, we refer to three terms S, M, and P, which are categorical terms, which stand for arbitrary predicates, like in functional programming, like in programming in Scala, and so forth. And this Barbara syllogism says that if all M are P and all S are M, then we can conclude that all S are P, which seems like a valid argument. If we recast this logic argument in terms of first order logic, what we will have is that we had to talk about entities of our domain of discourse. And we have to talk about, we had to talk about predicates. And predicates in this case are the things that we say of some entity, and we had to use universal quantifiers in this case. Okay. So, for instance, the major premise of the Barbara syllogism, all M are P, would be translated into first order logic as the proposition for all x, if n of x, then p of x. Okay. So again, we want to do the same. We want to use a Scala in order to show that this logic argument, the Barbara syllogism, is correct, is valid, is a correct, is a valid deduction, it's a logical deduction. How do we do that? Well, first of all, we need there will be propositions involved, and propositions we can reuse all the mappings that we already see from types and propositional connectives and implication, okay, into function types. But now we have entities of our domain of discourse. We have predicates. How do we model this in a Scala? Well, entities of our domain of discourse, in our domain of discourse, will be modeled as objects. Okay? And concerning predicates, they will be modeled as member types. In Scala, when we are declaring a type of object, we can not only declare member variables, member methods, we can also declare member types. And these types say things about our particular instance. Okay? So we will use this feature of Scala to model predicates. What about the universal quantifier? The universal quantifier and about propositions made of predicates. Well, if we have P of X, then according to this mapping, okay, that predicates are modeled through member types, the proposition corresponding to this, the type corresponding to this proposition, okay, P of X, will be X dot P, which is a path-dependent type in Scala, which is called a path-dependent type. Concerning propositions, for all X, P of X means that for all entity in our domain of discourse, we can give a proof for P of X. We can give a proof. Okay, in programming terms, this means that we can have an instance for the type corresponding to that proposition. This is modeled as a function. For any x of which we can say p, then I can obtain a proof for x dot p, for the type corresponding to this predicate. Okay, so this is a dependent function type in Scala, and this is something that it was introduced, this particular syntax, in Scala 3. Okay? In Scala 2, we would be able also to do it, but with more verbosity. Okay, so let's go and try to model our example. Um, in order to, we had to start from the entities of in the domain of this course. What we have is that what we can do, we can say about a given entity in our problem is S, M, and P. These are the three things that we say of entities in the syllogisms of Aristotle. Okay, and in order to prove the Barbara syllogism or any syllogism, we start from two premises, the major and minor premises, and then we arrive to the conclusion. In our case, these premises are these effects of the logic are these universal quantified statements, propositions. So we have for all x, this will be something like for all x, for we, in Habitant is our next example, sorry. For all entities, what we have is, in our major premise, is that if we have m of x, then we have m p of x, which in Scala terms, these are path-dependent types x dot m and x dot p. Remember that x is an entity, and we can say of an entity S n R P. The minor premise, equivalently, is that if we have x dot x, then we have x dot m. And the conclusion would be something like this: x dot p. Okay? How do we implement this process? Again, using time-driven development and using the constructors and destructors for function-dependent types. But note that function-dependent types are very, very, very similar to function types. We need also, what we need is a lambda expression in order to create this function dependent function, this dependent function. And what we need is to extract information from this dependent function using function application again. Okay, so we will not precisely state which are the constructors and destructors for this new type of entities. Okay, the only difference between dependent function types and regular functions is that we can refer in the body of the function, we can refer to the input argument of the function. Okay, in this case, x. Otherwise, it's the same. So, which is the type of our whole? The type of our whole is this. Okay, and this is a dependent function. We create a lambda expression, which in this case is easier. We already had the name of the variable. Okay, and what we have to do is to obtain this conclusion, an expression of this type. But this is a regular function now. We have here is from x's, we have to obtain xp. Sorry. And now, how do we obtain xp? In order to obtain xp, x.p, our only chance is to use the major premise. The major premise, as you see, allow us to obtain s.p. How do we reach this conclusion? Well, notice that in order to reach this function and the body of this function, we need to apply the major premise. So if we apply the major premise to x, to our x, then what we obtain is a function, and a function from x dot n to x dot p. And if we apply x dot m, what we obtain is x dot. How do we obtain x dot m? Again, using the minor premise, if I would be able to obtain an xs, then I will be able to obtain xm. And again, xx, I obtain here. Okay? And this would be our implementation. Of course, this can be polished, and we can remove all this information here, all these type annotations, and we would obtain. In type-driven development, the types are very useful to guide the development process. But once we finish the process, we can remove many of these. From here, what we can do as well is to compose major X with minor X. Okay? And we obtain a better proof even. Okay? So this is an example of syllogism in which all the major premise and the conclusion are universal categorical statements. We have also the possibility of finding syllogisms in which we have particular statements, like some M are not P in the Bocardo syllogism. If some M are not P, if all M are S, then some S are not P, which also seems like a valid argument, because if all M are S, some M will be, all these M will be S, and some S are not P. We can also implement a signature that shows that this syllogism is valid, that this kind of reasoning is valid. But for that, what we need is to model not only the universal quantifier in first order logic, but also the existential quantifier, because the major premise is formalized in first order logic as exists an X, an entity in our domain of discourse, for which n of X and not P of X. Okay. And how do we model this in Scala? For that, what we need is to, when we say in logic, in constructed logic, that we have a 6x such that P of x, what we are saying is that we have found an entity in the domain of discourse. Okay, for this entity, we have a proof that P of x. Okay. So in programming terms, this means that that the type corresponding to this existential type has to provide us with an object that represents the entity of the domain of discourse that we found, and a proof that the type corresponding to P of x is valid. So what we have here is simply a record with two members, with two member values, an x, of which we can say p, and a proof that p of x, that x dot p. Okay. And this is called in the type system literature as a dependent sum type. I will leave you this exercise, this as an exercise for you to enjoy and practice, and simply know that if we apply this mapping, and okay, the major premise will be value x, this will be an entity, and here we will have a proof that a conjunction from x dot m, okay, and not x dot p. Okay, this will be the first premise. This would be the second one, will be for any entity. What we have here is a function, x dot m, x dot s. And the conclusion will be again a dependence on type, an entity, and a proof. prove that X is and not XP. Okay? We may go and try to implement the signature, but if we do this, literally, we will run into some issues regarding singleton types and immutable paths and so forth. So this is a workaround which simply consists of the representing this existential type in particular with a regular trait instead of a structural type. Okay, but with this, you will be able, without any problem, to complete the implementation. Okay, so let's go for our next example, which is really nice, and this will lead us into second-order logic. We will show an example in propositional logic. We dealt with first-order logic quantifier, this is essential and the universal quantifier, and we will see now that there are some second-order features in this case. The problem that the logic problem that we will attempt to solve using Scala or formalize using Scala is one of the logic puzzles by Raymond Smullyan, who was a very famous logician who also wrote many recreational books on logic. And it is really fun to pick up one of these logic puzzles and try to formalize the solution using a Scala. In this case, what we will use is a puzzle from the series of knights and knaves. Knights and knaves are inhabitants of an island, and which well, in this island, these inhabitants that could be knights and knaves. Knights always tell the truth, and knaves always lie. They are persistent liars. Okay. Given these premises, of the game, this is the setup for all these logic puzzles. This particular puzzle that we are going to formalize the solution is the following: is it possible for any inhabitant of this island to claim that he's a knave? Well, given these premises, since any inhabitant is either a knight or a knave, if he would be a knight, he couldn't say that he is a knave because he would be lying. And knights always tell the truth. And if he would be a knave, he would be telling the truth, but knaves never tell the truth. So the answer is that no, it's not possible. If we assume that some inhabitant is saying this, then we reach a contradiction. Okay. How do we implement this in Scala? First, let's consider how do we implement this, how to formalize this in logic, in first-order logic, and in this case, second-order logic. Why? Because the first premise is easy. For any entity in our domain of discourse, which are inhabitants, for any inhabitant, what we have is that either X is a knight or he is a knave, where knave means that he is not a knight. Okay? This is first order logic, regular first order logic. But for the second and third premises, knights always tell the truth and knaves are persistent liars. We need second order features. What does it mean? Well, what it means is that in this case, what we are saying is that if any inhabitant, if some inhabitant is a knight, then everything, any kind of thing that she says, it will be true. Anything that she says is a proposition. Okay, so for any proposition, if X claims this proposition, then it is actually true, which means that we have a proof of P. And if our inhabitant is a knave, it is the opposite. If X, this inhabitant claims P, then what we have is that this inhabitant is lying, which means that we can prove not P. Okay? And this is holds for any kind of P. Okay? And concerning this particular puzzle, this is about the premises of our game. And for this particular puzzle, what it's saying is that it is possible for an inhabitant of this island to claim that he's knave. What he says is for all inhabitants, it not says if X says that he is a knave, then we obtain a contradiction, which means that for x not says x knave x. Okay? So, uh, how do we model these second order features using type constructors? Okay? These second order features, what means is that, for instance, this predicate says receive as argument an individual, but also a proposition. So we have here a kind of second order predicate. And what we have here is something like given a proposition, it will return a proposition. In terms of programming, it is something that if it is given a type, it will return a type, which is a type constructor. Okay. If we have a second order predicate and that receive a particular proposition, we have P and Q, the type constructor application. And if we have a universal proposition, which is made of a universal quantification over propositions, what we have here is a new feature in Scala 3, which are polymorphic function values. Okay. So let's go and implement our gain. In this case, we first start with our domain of this course, the inhabitants, and what we say about inhabitants are that they are knights, that they are knaves, means that they are not knights, and that inhabitants may say something, says P, okay, say something. Now, about the premises. About the premises, what we can hear is that for all inhabitants, we have either knight or slave. And here, what we have is universal quantification both for inhabitants and for propositions. I move here in front of the formula the quantification for the proposition, okay? Because I was having problems. It was in the middle, and I didn't have time for looking for workaround. What it was exactly happening. So if we have any proposition, any inhabitant, okay, if this inhabitant is a knight and it says P, then P. And in the case of knaves, what we have is we have X is a knave. If X says P, what we have is not P. Okay? And now our puzzle, oh, we knave. Okay? In our puzzle, how do we implement the conclusion? The conclusion says that for all inhabitants, any inhabitant can say that he is a knave. Okay? How do we solve this problem? Again, using type-driven development. But in this case, what we want is we already have the demonstration. We already have, and the gain in this case is not to come up with a new demonstration, but to being able to resemble this particular demonstration in Scala. And the Scala says, in the demonstration says, the proof says that for any inhabitant, inhabitant could be, according to premise one, it could be a knife or a knave. Okay, if he is a knight, we have, of course, to reach out in conclusion. If he is a knave, okay. What we have here is we have an inhabitant. We have to conclude this, and this means that says we have to reach a contradiction from. Okay. And in this case, what we have is that if we have a knight, by premise 2, okay, what we have is for x, given that x is a knight and says these things, what we obtain here is that x is knave. Why? Because x is a knight, and and say the truth. And what he is saying is that X naive. Okay? But if we have that a proof that X is a knight and it is a knave, since X knave is X knight means not X knight, what we have here is a contradiction, the contradiction that we are looking for. Okay? And similarly for this branch. Okay? And it's time to finish. I will leave you this as an exercise to finish this. And also, I will leave as an exercise how to improve this proof in such a way that it matches more closely the, uh, the proof that we want to model. Okay, what we would like is to be able to write an Scala program that it is as closely as possible to as close as possible to the demonstration. And for that, what I provide you is with some useful auxiliary functions, some syntactic sugar. For instance, claiming that obtaining nothing in a more readable way from not P and P, to use the premises in such a way that we do not have to um, refer explicitly to the premises of the game. And for instance, here to facts that if we have in scope that X is a knight, then we would like to remove this argument and receive this argument implicitly. We can do this using context-dependent functions in Scala. Okay, this is also a nice exercise to come up with a more beautiful proof and more and closer to the proof that we were implementing. Okay, so let's conclude. What can we learn from all these exercises? Well, what we can learn in our propositional logic example, what we can learn is we can learn to take type signatures seriously and to exercise type-driven development. This is something that in our every day as a programmer, when we are using cats or we are using a functional programming library like Casbo, we are using aka HTTP or HTTP for Scala, web frameworks, database libraries, and so forth, we will encounter time and again a lots of signatures, and we will find tuples and adders and functions, higher order function, and so forth. Doing these exercises, these proving propositional tautologies using Scala, will get you used to tight signatures, and you will get used to type-driven development, and it is a really nice exercise. Okay. With syllogisms, we introduce dependent types, path-dependent types. It's also a very nice modeling example, and the same for Smullyan's knights and knife puzzles. We use polymorphic function values in the case of this second-order logic puzzle, but it is I mean, it is not completely necessary because we may use here a polymorphic method. Okay, if we model this exactly like it is set here, then we will definitely use a polymorphic function. But in this case, it was not the very best example. Okay. But still, we had the chance to practice with this polymorphic function method. In general, it is fun to solve these logic problems using Scala, to solve these tautologies or picking up one problem, logic problem from Raymond Smullyan. It is really fun to codify this in Scala. You learn a lot also from the point of view of modeling, not only from the point of view of practicing and learning these Scala features like dependent function types and polymorphic function values and so forth. Okay, this means that Scala is the ideal language for doing theorem proving. No, we didn't claim that. What we are only claiming is that we can learn a lot from logic problems. If you need to do specific theorem proving, then you need specialized languages for that, like Coq, Acta, and so forth. Okay, but still trying to implement these logic problems will gives you a lot of information about the limits also of the Scala feature, the limits of path-dependent types and so forth. So it is really interesting. Okay. Well, I will leave you here with some reference for this GitHub repo where we intend to implement the proofs for the 24 valid syllogisms of Aristotle. Please feel free to contribute. It is fun to do this. As I said, you are also invited to pick up one of the books from Raymond Smullyan and try to implement these puzzles. You have also this reference about functional programming in general, type-driven in development in particular, using Idris. Okay, there is also this really nice talk about the Curry-Howard correspondence by Sergei Vinitsky, which is the author of a plugin for Scala 2 for doing these all demonstrations automatically. Okay, and you have also this the repo for this talk. Well, you will find the notebook that I use. Okay. Finally, thank you very much for attending, and see you. I hope to see you soon. And if you can by Madrid, please say hi. Okay, that's all. Thank you.
Fire in retro rock.
Roger, Matt. Ready to eject.